Imagine standing on the surface of Mars 2 years from now. You're not there in person, of course, but through the sensors and cameras of a humanoid robot, watching through its digital eyes as metallic fingers dig into the rust-colored soil. The machine's chemical analyzers detect something unusual, something that shouldn't exist in this sterile environment. Elevated concentrations of nickel in a specific isotopic ratio. Complex organic compounds showing structural patterns that don't match any known Martian mineralogy. And frozen crystals of hydrogen cyanide mixed with water ice at depths that suggest recent deposition. The robot doesn't understand the significance of what it has found. Its neural networks register the data as anomalous, flag it for further analysis, and continue with the primary mission objectives. But when that data reaches Earth, when human scientists examine the spectroscopic signatures and cross-reference them with historical records of interstellar object trajectories, they understand immediately. This is the delivery. The cosmic payload dropped off by an object from another star system that passed this world just 14 months before the robots arrived. This isn't science fiction. This isn't speculative fantasy or wishful thinking by enthusiasts searching for evidence of extraterrestrial contact. This is the emerging story of 3I/Atlas, an interstellar comet that swept past Mars at a distance of 29 million kilometers in October 2025. Releasing a precisely balanced cocktail of water, nickel, and cyanide. The exact molecular recipe for metalloproteins, those hybrid structures where biology and technology blur into one unified system. Every claim made in this investigation is backed by published observations, peer-reviewed papers, and data from the world's most sophisticated astronomical instruments. The chemistry is real. The trajectory is documented. The timing is verified. What remains open to interpretation is the meaning, the question of whether we're witnessing an extraordinary natural phenomenon or something that carries the fingerprints of ancient intelligence. In the vast darkness between stars, objects travel for millions of years. Comets ejected from their home systems by gravitational perturbations. Planetary embryos cast out during the chaotic formation of solar systems. Perhaps even deliberately constructed probes launched on trajectories calculated to intersect with younger stellar environments. Most pass through our solar system completely unnoticed, too small and dark to reflect enough sunlight for detection. Invisible wanderers from distant stellar nurseries that enter our gravitational neighborhood and depart without ever registering on human instruments. But occasionally, one announces itself with spectacular chemistry. 3I/Atlas did exactly that when astronomers first tracked its trajectory in July 2025. The discovery itself was routine, an automated survey picking up an object with unusual motion against the background stars. But within days of confirmation, as observatories around the world turned their instruments toward the newcomer, the data began revealing anomalies that defied conventional cometry science. This wasn't an ordinary comet. From the moment observatories locked onto it, the spectroscopic data revealed a chemical composition and activity pattern that broke multiple established rules about how comets behave. The object was hemorrhaging water at a rate of 40 kilograms per second, a mass loss equivalent to 88 pounds every single second of every minute of every hour. To put that in terms that make intuitive sense, imagine a fire hose running at full blast, the kind firefighters use to combat industrial fires. Now imagine that hose has been running continuously, without pause, since early summer. The numbers become almost absurd when you calculate the cumulative outflow. 144 metric tons every single hour. 3,456 metric tons every day. That's enough water to fill an Olympic-sized swimming pool. Those massive competition venues that hold 2.5 million liters. every single day for months. The sheer volume defied models. Comets do release water as they approach the sun, as solar heating warms their icy surfaces and sublimates frozen volatiles into space. But the rate depends on distance from the sun, on surface area, on how much energy the comet is absorbing. 3I Atlas was producing water at rates that suggested either an extraordinarily large nucleus, far larger than its optical brightness indicated, or an unusual composition where water was exceptionally volatile, able to sublime at lower temperatures than normal ice. But water, as remarkable as that outflow was, turned out to be just the beginning. When the Keck Observatory in Hawaii turned its powerful instruments toward 3I Atlas in late August, specifically deploying the cosmic web imager designed to detect faint emission lines from distant astronomical objects, they discovered something that, according to 70 years of cometry science, simply shouldn't exist in nature. Pure nickel emission without any corresponding iron signature. In the universe we know, in the cosmos mapped by spectroscopy and planetary science and meteorite analysis, nickel and iron are siblings born together in supernova explosions, traveling together through space in roughly consistent ratios. Every comet we've ever analyzed, every asteroid we've studied, every chunk of cosmic debris from meteorites to samples returned from asteroid missions shows both elements together. The ratio might vary slightly depending on the formation environment, but they are always both present. Iron typically dominates, comprising about 90% of the iron-nickel mix, with nickel making up the remaining 10%. It's one of the most reliable patterns in cosmochemistry. The separation of nickel from iron, the ability to observe one element without the other in emission spectra, is known to humanity. We've mastered it in industrial settings, but that knowledge exists only in one context: metallurgical refinement facilities using the Carbonyl process, a technique invented in the late 19th century by Ludwig Mond. The process is elegant in its chemistry. You take impure nickel ore, metal mixed with iron and other contaminants, and expose it to carbon monoxide gas under specific conditions. Temperatures around 50 degrees Celsius and modest pressures. The nickel reacts preferentially with the CO to form nickel tetracarbonyl, a volatile compound that evaporates away from the solid material. You collect that vapor, separate it from the remaining solid ore that still contains iron and other metals, then heat the nickel tetracarbonyl to higher temperatures. The compound decomposes, breaking apart to deposit pure nickel metal while releasing carbon monoxide gas that can be recycled back into the process. It's how we've refined this metal since the early 20th century, how we produce the high-purity nickel used in electronics, in stainless steel, in batteries for electric vehicles. It's industrial chemistry, human technology, a process invented to solve specific problems in materials science. And now, apparently, it was happening naturally on an interstellar comet. Or perhaps, and this is where the speculation begins to intersect with data in uncomfortable ways, not naturally at all. The third component of this delivery was simultaneously the most familiar and the most intriguing from a biological perspective. Hydrogen cyanide, flooding from the comet's nucleus at exponentially increasing rates as it approached the inner solar system, following a production curve so steep that it suggested autocatalytic chemistry or cascading release mechanisms rather than simple thermal sublimation. To most people, to anyone who has encountered the term in crime novels or historical accounts of wartime atrocities, cyanide means poison. It means death, a lethal compound that shuts down cellular respiration within minutes by binding to the iron centers in cytochrome C oxidase, the enzyme complex that allows mitochondria to use oxygen for energy production. Block that enzyme and your cells suffocate from the inside, unable to process oxygen even as your lungs continue breathing. It's efficient at killing, precisely because it targets the machinery of life at the most fundamental biochemical level. But to astrobiologists, to researchers studying the origin of life and the chemical pathways that led from simple molecules to self-replicating systems, cyanide is a builder molecule. It's one of the most important prebiotic compounds we know, a chemical that under the right conditions can assemble itself into the precursors of life through well-documented reaction pathways. Back in the 1950s, Stanley Miller and Harold Urey conducted one of the most famous experiments in the history of origin of life research. They sealed simple gases into a flask, gases thought to represent Earth's early atmosphere: methane, ammonia, water vapor, and hydrogen. They ran electrical sparks through the mixture, simulating lightning strikes or ultraviolet radiation from the young sun. After just 1 week, the flask contained amino acids, the building blocks of proteins, molecules essential to all known biology. When researchers analyzed the reaction pathways, when they traced how simple gases became complex organic molecules, they found that hydrogen cyanide was a critical intermediate. The electrical energy broke apart the simple molecules. The fragments recombined, and among the products was HCN. That cyanide then participated in further reactions, building more complex structures through well-characterized chemistry. Later research, particularly work conducted at the Scripps Research Institute in the early 2000s, demonstrated that cyanide acts as a reducing agent in primitive metabolic pathways. It can drive the formation of organic molecules that in modern biology require complex enzymes with sophisticated active sites. But in the prebiotic environment, in the chemical soup that existed before there were cells or genes or evolution, cyanide could do it alone or with simple metal catalysts. It could build nucleotide precursors, the components that eventually became RNA and DNA. It could synthesize amino acids through multiple pathways. It could even participate in primitive versions of metabolic cycles, sequences of chemical reactions that extract energy from simple compounds. Cyanide is toxic to complex life precisely because it's so good at chemistry, so reactive and versatile. It binds to metal centers in enzymes, disrupting the carefully evolved machinery of metabolism that took billions of years to develop. But before there were cells to poison, before there were enzymes to disrupt, before there was sophisticated biochemistry that could be derailed, cyanide was one of the molecules assembling the very structures that would eventually become life. It's the ultimate paradox of prebiotic chemistry. The molecule of death is also the molecule of creation. Now consider with that background what 3I/Atlas was releasing as it made its close approach to Mars, as it swept through the inner solar system on its hyperbolic trajectory. Water, the universal solvent, the liquid medium in which all biochemistry as we understand it occurs. Water that can dissolve polar molecules, that can shuttle ions, that provides the three-dimensional environment where complex molecules can encounter each other and react. Nickel, a catalytic metal that sits at the heart of some of the most ancient enzymes in biology. The proteins that enable primitive metabolism in oxygen-free environments, that allow organisms to extract energy from simple gases like hydrogen and carbon dioxide. And cyanide, the prebiotic molecule that builds organic complexity through well-documented reaction pathways studied in laboratories around the world. Together, these three components cover both sides of the equation that any self-sustaining chemical system requires. They provide matter and energy, raw materials and catalysis, building blocks, and the means to organize those blocks into increasingly complex structures. This wasn't a random assortment of volatiles, the kind of mixed chemistry you'd expect from a comet formed in the outer regions of a planetary system, where different ices condense at different temperatures. This was a focused, coherent chemical system, a complete starter kit, The trajectory of 3I Atlas, the path it followed through three-dimensional space as it entered our solar system and swept past Mars, raises questions that pure chance, that random gravitational perturbations and ballistic physics, struggles to answer convincingly. Space is vast. It's three-dimensional, with no preferred orientation. No up or down. No natural plane that objects must follow. When astronomers detect interstellar objects, when we spot comets or asteroids that originated outside our solar system, they typically arrive on steeply inclined trajectories. They dive through the planetary plane from above or below, at angles measured in tens of degrees, sometimes approaching perpendicular incidents. This makes intuitive sense. They were ejected from their home systems in random directions, traveled through the galaxy along paths determined by their initial velocity and the gravitational influence of nearby stars, and happened to intersect our sun's gravitational sphere of influence from whatever direction they were traveling. But 3I/Atlas arrived on a path roughly aligned with the ecliptic plane, that flat disk where all the major planets orbit, where Earth and Mars and Jupiter trace their yearly paths around the sun. The inclination, the angle between the comet's orbital plane and the ecliptic, was measured at just a few degrees. Most interstellar visitors show inclinations of 30, 40, 50 degrees or more. The probability that a randomly oriented object would arrive aligned this closely with our planetary system's fundamental plane purely by accident has been calculated by multiple research teams. The answer depends on your exact definition of closely aligned. But for an inclination within 5 degrees, you're looking at approximately 1 in 50, a 2% probability. Already uncomfortable territory for coincidence, but not impossible. Rare events happen. With thousands of interstellar objects potentially passing through the solar system over millions of years, a 2% probability eventually manifests. You could dismiss the ecliptic alignment as luck, but the precision goes much deeper than just arriving in the right plane. The comet's closest approach to Mars occurred on October 3, 2025, at a distance of 29 million kilometers. For that specific encounter to happen, for 3I Atlas to pass that close to Mars at that particular moment, requires not just being in the right plane, but arriving at precisely the right time. Mars takes 687 Earth days to complete one orbit around the Sun. It moves at an average velocity of 24 kilometers per second, covering about 2 million kilometers per day in its elliptical path. If 3I Atlas had arrived a month earlier or a month later, just 30 days of difference in a journey that potentially lasted millions of years, Mars would have been somewhere else entirely, 60 million kilometers away in its orbit. The close approach wouldn't have occurred. Avi Loeb, the Harvard astrophysicist who has built significant portions of his recent career on asking uncomfortable questions about interstellar objects and refusing to dismiss anomalies simply because they suggest unusual conclusions, calculated something called the minimum orbit intersection distance for 3I Atlas and Mars. This MOID represents the closest the two orbital paths come to touching in three-dimensional space, not where the objects themselves were at any given moment, but where their trajectories as geometric curves approach most closely. For 3I Atlas and Mars, that minimum orbit intersection distance was 2.7 million kilometers. That's the distance you'd have to move one of the orbits, either raising or lowering it slightly, stretching or compressing it marginally, to make the two paths actually intersect. In the context of the solar system, where planetary orbital distances are measured in hundreds of millions of kilometers, 2.7 million is tiny. It's close, uncomfortably close. For a natural object on a hyperbolic trajectory, an object that's not orbiting the Sun, but falling past it on a path determined entirely by where it came from and how fast it was moving when it entered the heliosphere. an object with no means of course correction, no engines or thrusters or controlled outgassing. To thread that needle, to arrive on a path that misses intersecting Mars's orbit by such a small margin, requires either extraordinary luck or something else. Something that involves planning, calculation, or at minimum, a physical process that can guide trajectories with precision. The origin point adds yet another layer of mystery to this already puzzling object. Trajectory analysis, the process of working backward from observed positions and velocities to determine where something came from, suggests that 3I Atlas originated from the direction of Sagittarius, from the thick disk of the Milky Way, where stellar populations are fundamentally different from our solar neighborhood. Our Sun is a member of what astronomers call the thin disk, a population of relatively young stars. Stars formed within the last few billion years from gas clouds enriched by multiple generations of earlier stellar evolution. These stars, including ours, have high metallicity in astronomical terms, meaning they contain substantial fractions of elements heavier than hydrogen and helium. That metal enrichment came from supernovae, from massive stars that fused lighter elements into heavier ones, and then exploded, seeding the interstellar medium with carbon, oxygen, iron, nickel, all the elements essential for rocky planets and complex chemistry. But the thick disk, the population from which 3I Atlas likely originated based on its velocity vector and galactic trajectory, contains much older stars. These are systems formed 7 to 10 billion years ago, when the universe was younger and the interstellar medium was less enriched with heavy elements. Stars from that population have lower metallicity, different elemental abundances, planetary systems that formed from chemically distinct protoplanetary disks. If you were an ancient civilization, if you had developed technology billions of years ago in a star system that formed when the galaxy was young, and you wanted to seed younger planetary systems, systems that might one day develop their own technology and join you as peers or successors, you would launch from exactly such a mature stellar environment. You would target systems like ours, yellow dwarf stars with the potential for Earth-like planets, stars young enough that complex life might be emerging but haven't yet filled their planets with technological civilizations. This is speculation, absolutely, but it's speculation grounded in the actual measured properties of 3I Atlas, in data from world-class observatories, in trajectory calculations performed by respected astrophysicists. The question isn't whether we can invent a scenario that fits the data. The question is whether the natural alternative, pure chance, remains the most reasonable explanation when the improbabilities start to multiply. Inside your body right now, at this very moment as you read these words, there's a molecular machine that represents the fundamental partnership between organic chemistry and raw elemental matter, between the complex carbon-based molecules of biology and simple metallic atoms forged in the hearts of dying stars billions of years ago. Hemoglobin, the protein responsible for oxygen transport in your bloodstream, for capturing oxygen molecules in your lungs and delivering them to cells throughout your body, is built around 4 iron atoms arranged in a precise geometric configuration. Each iron atom sits at the center of a structure called a heme group, a flat ring of carbon and nitrogen atoms that cradles the metal. When oxygen binds to that iron, the metal's electronic structure changes slightly, altering the shape of the entire protein. That shape change is what allows hemoglobin to regulate its oxygen affinity, to pick up oxygen in the high concentration environment of the lungs and release it in the low concentration environment of tissues that are actively consuming oxygen for energy production. Remove those 4 iron atoms, extract them from the heme groups through chemical treatment, and the protein becomes completely useless. It's still there, still folded into its complex three-dimensional structure, still a chain of amino acids 141 residues long. But it can't bind oxygen. It can't transport anything. It becomes just a molecular sculpture, aesthetically interesting perhaps, but functionally dead. The metal is what makes it work. The metal is what makes it alive in any meaningful sense. This is the reality of metalloproteins, the class of proteins that require metal cofactors for function. Current estimates suggest that roughly 1/3 of all known proteins fall into this category. Iron in hemoglobin and myoglobin for oxygen transport and storage. Copper in cytochrome C oxidase for the final step of electron transport that generates most of your cellular energy. Zinc in DNA polymerase for copying genetic information. In carbonic anhydrase for managing carbon dioxide in your blood. In hundreds of transcription factors that regulate gene expression. Manganese in superoxide dismutase for protecting cells from oxidative damage. Molybdenum in enzymes that metabolize sulfur compounds. Cobalt at the center of vitamin B12, essential for DNA synthesis and neurological function. And, critically for our story, for understanding what 3I Atlas might have delivered, nickel at the heart of some of the most ancient enzymes in biology. Nickel-dependent enzymes aren't as familiar as iron or zinc proteins. You don't learn about them in high school biology. They don't appear in the standard textbook examples of metalloprotein function, but they're profound in their implications, because they represent some of the oldest biochemistry we know. Molecular machines that were already sophisticated 4 billion years ago, when life was just emerging from whatever prebiotic chemistry preceded it. Hydrogenases, enzymes that catalyze the reversible splitting of molecular hydrogen, the reaction that converts H2 into 2 protons and 2 electrons, depend absolutely on nickel-iron active sites. These enzymes are found in methanogens, microorganisms that live in oxygen-free environments and produce methane as a metabolic byproduct. They're in some bacteria that use hydrogen gas as an energy source, oxidizing it to extract electrons for cellular processes. The nickel sits right at the catalytic center, coordinated by sulfur atoms and positioned perfectly to activate hydrogen molecules. Remove the nickel, and hydrogenase stops working. The enzyme can't split hydrogen anymore. The organism loses its ability to metabolize that particular substrate. The nickel isn't decorative. It's not a structural element that just happens to be there. It's the functional core, the atom that does the actual chemistry. There's also carbon monoxide dehydrogenase, another nickel-dependent enzyme with profound implications. This protein catalyzes the oxidation of carbon monoxide to carbon dioxide, a reaction that releases electrons and energy. But it can also run in reverse, taking CO2 and reducing it to CO, or even further to organic carbon compounds. It's a key component of what's called the acetyl-CoA pathway, one of the most ancient metabolic routes known. A sequence of reactions that allows organisms to grow on nothing but hydrogen gas and carbon dioxide, the simplest possible inputs. Organisms using this pathway don't need organic molecules from their environment. They don't need sugars or amino acids or any complex compounds. Give them H2 and CO2, two gases that were abundant on early Earth, that bubble out of hydrothermal vents, that exist in volcanic emissions, and they can build everything else they need. They can synthesize all the organic molecules required for life, starting from the most primitive precursors. And the enzyme that makes this possible, the protein that captures and fixes carbon dioxide, has nickel at its active site. The presence of nickel in these ancient enzymes tells us something fundamental about early life. It tells us that when biology was first emerging, when the earliest metabolisms were being shaped by chemical availability and thermodynamic constraints, nickel was there, was essential, was being incorporated into proteins that performed chemistry no other metal could manage as efficiently. Now, fast forward 4 billion years from those ancient metabolisms, from those primitive organisms living in hydrothermal vents and using hydrogen and carbon dioxide as their sole energy sources. Modern biology has become extraordinarily sophisticated. We have complex multicellular organisms, elaborate nervous systems, consciousness and culture and technology. But underneath all that complexity, underneath the millions of genes and thousands of cell types and intricate developmental programs, the ancient nickel-dependent enzymes are still there, still functioning, still essential. Methanogens still use hydrogenase. Acetogenic bacteria still use the acetyl-CoA pathway with its nickel-containing carbon monoxide dehydrogenase. These organisms represent living fossils in biochemical terms, lineages that have maintained metabolisms remarkably similar to what existed billions of years ago. And when we analyze their enzymes, when we solve the three-dimensional structures of their metalloproteins using X-ray crystallography or cryo-electron microscopy, we see nickel atoms at the active sites, coordinated by amino acid residues in precisely the arrangements required for catalysis. The connection becomes clear, becomes almost uncomfortable in its implications, when you consider what 3I Atlas delivered to Mars. Nickel that can serve as catalytic centers in primitive metabolic enzymes. Cyanide that can build organic precursors through prebiotic chemistry. Water that provides the medium where both processes can occur. Together, they represent a complete chemical foundation, not necessarily for Earth-like biology, with DNA and RNA and complex proteins, but for something that occupies the gray zone between pure chemistry and what we call life. These are the building blocks for metalloproteins, for hybrid structures where inorganic metal cores and organic molecular scaffolding combine to create function that neither component possesses alone. And metalloproteins are already the proof, the existing demonstration in terrestrial biology, that the boundary between the inorganic and organic worlds isn't absolute. It's permeable, negotiable, a spectrum rather than a sharp division. When you picture a comet in your mind, when you imagine one of these icy wanderers from the outer solar system making its close pass by the sun, you probably visualize a bright nucleus, a glowing head maybe a few kilometers across, and streaming behind it a tail of dust, particles reflecting sunlight and creating those spectacular images that grace magazine covers and astronomy websites. But there's another tail, one that's invisible to the naked eye. One that doesn't show up in standard optical photographs, but reveals itself only through specialized instruments that can detect ionized gas and measure magnetic fields. This is the plasma tail. And for understanding what 3I Atlas might have delivered to Mars, it's arguably more important than the visible dust tail. Plasma is matter in its fourth state, beyond solid, liquid, and gas. It's what you get when energy, whether from high temperatures or intense radiation or electrical currents, strips electrons away from atoms, leaving a soup of positively charged ions and negatively charged electrons, all moving independently, rather than bound together in neutral atoms. The sun is plasma throughout its entire volume. Hydrogen and helium so hot that electrons can't stay attached to nuclei. Lightning is a channel of plasma. Air heated and ionized by electrical discharge. And the region immediately surrounding an active comet, bathed in intense ultraviolet radiation from the sun, becomes plasma too. As 3I Atlas moved through space, as it approached the sun and solar heating increased, the comet began shedding its inventory of volatiles: water molecules, carbon dioxide, carbon monoxide, hydrogen cyanide, and nickel vapor from whatever process was releasing that metal preferentially over iron. These neutral molecules and atoms entered the surrounding space, moving outward from the nucleus driven by sublimation pressure and gas dynamics. But they didn't stay neutral for long. Solar ultraviolet radiation, photons with enough energy to break chemical bonds and strip electrons from atoms, ionized this outflowing gas. Water molecules became H2O plus ions. Carbon dioxide became CO2 plus ions. Hydrogen cyanide became HCN plus, or broke apart into CN plus fragments and hydrogen atoms. Nickel atoms, already volatile and reactive, lost one or more electrons to become Ni plus or Ni2 plus ions. Once ionized, these particles stopped behaving like simple gas molecules, following ballistic trajectories. They became responsive to electromagnetic fields. The solar wind, that constant stream of charged particles flowing outward from the sun at velocities between 400 and 800 kilometers per second, swept them up. The sun's magnetic field, carried by the solar wind and extending throughout the heliosphere, guided their motion. And the result was a tail, an ionized tail stretching potentially millions of kilometers behind 3I Atlas, invisible to optical telescopes, but detectable through its interaction with magnetic fields and through the emission of light at specific wavelengths as ions recombined or transitioned between energy states. Here's what makes this plasma tail profoundly significant for our story. Plasma doesn't just flow passively like water down a river. It has structure. It develops filaments, regions of higher and lower density. It generates waves, oscillations that propagate through the ionized medium at speeds determined by the magnetic field strength and the ion mass. It exhibits instabilities, turbulence, patterns that emerge from the complex interplay between particle motion and electromagnetic forces. These patterns carry information, not encoded data like a computer file, not bits and bytes deliberately arranged to convey meaning, but physical information embedded in the geometry. The arrangement of particles in three-dimensional space, the topology of magnetic field lines that thread through the plasma, the propagation of waves, their wavelengths and frequencies and directions of travel. All of this constitutes information in the physics sense, a structured state that's different from random noise, that has lower entropy than a completely disordered system. Mars, unlike Earth, doesn't have a global magnetic field anymore. It lost that protective shield billions of years ago when its molten iron core cooled and solidified, when the dynamo effect that generates planetary magnetic fields shut down. But Mars does have two types of magnetic structures that remain significant: localized crustal magnetization and an induced magnetosphere. The crustal magnetization consists of patches of ancient magnetic field, frozen into rocks that formed when Mars still had a global field. These patches are particularly concentrated in the southern highlands, in the oldest terrain on the planet, Noachian age crust dating back 4 billion years. The frozen fields aren't uniform or organized like Earth's dipole field. They're patchy, irregular, with strengths that vary significantly from region to region. But they're real, they're measurable, and they interact with charged particles. The induced magnetosphere is different. It's not a remnant from the past, but a structure that forms dynamically as the solar wind interacts with Mars's upper atmosphere. The solar wind carries the sun's magnetic field with it. When that magnetized plasma encounters Mars, It doesn't hit a global magnetic barrier like it does at Earth. Instead, it interacts directly with the atmosphere, piling up on the day side, compressing, generating electric currents. Those currents create their own magnetic fields, which push back against the solar wind. The result is a magnetic bubble, a magnetosphere induced by the solar wind interaction, rather than generated by the planet itself. Both of these structures, the crustal magnetization and the induced magnetosphere, can channel plasma. They can guide charged particles, funnel them along field lines, concentrate them in specific regions rather than allowing uniform deposition across the entire planet. Think about how a cathode ray tube works. Those old television and computer monitors from before flat panel displays became dominant. You don't just spray electrons randomly at a phosphorescent screen and hope they light up useful pixels. You steer them with magnetic fields, using precisely controlled electromagnets to deflect the electron beam horizontally and vertically, focusing it into precise spots that create an image. The magnetic fields act as lenses and guides, routing charged particles along predetermined paths. The same principle applies at planetary scales. If the plasma trail behind 3I/Atlas carried a net charge, if it had internal structure with regions of different ion densities or different dominant species, the Martian magnetosphere, both crustal and induced, could act as a natural lens. It could concentrate the delivery, funnel nickel ions and cyanide molecules and water ions toward the surface in patterns determined by the magnetic topology. Not uniform deposition across the entire planet, but targeted deposition in specific regions where magnetic field lines converge, where the geometry channels particles downward. This isn't science fiction or wishful speculation. This is plasma physics, a well-established field with decades of research and comprehensive mathematical frameworks. We see similar effects in Earth's aurora, those spectacular light displays in polar regions, where charged particles from the solar wind and magnetosphere follow magnetic field lines down into the upper atmosphere. The particles collide with oxygen and nitrogen molecules, exciting them to higher energy states. When those molecules de-excite, they emit light at characteristic wavelengths, green from oxygen, red from nitrogen, creating the shimmering curtains and arcs we call the northern and southern lights. On Earth, the thick atmosphere intercepts those particles at altitudes of 100 to 400 kilometers. The particles never reach the ground. They dump their energy into atmospheric gases, creating light and heat. But they don't modify surface chemistry. On Mars, with its thin atmosphere only about 1% the density of Earth's, charged particles can penetrate much deeper. They can reach the surface, especially in regions where the atmospheric column is thinner, like in elevated terrain, or during nighttime when the upper atmosphere cools and contracts. When those particles hit the surface, when ions impact dust grains or ice particles or rock surfaces, they don't just bounce off. They interact. They transfer energy. They embed themselves at the nanometer scale through a process called ion implantation. This is known physics used routinely in semiconductor manufacturing, where ion beams are accelerated and directed at silicon wafers to create doped regions with specific electrical properties. The ions penetrate a few nanometers to a few micrometers, depending on their energy, becoming part of the surface material's chemical composition. It happens naturally, too. Cosmic rays, high-energy particles from supernovae and other energetic sources, bombard asteroids and modify their surface chemistry through ion implantation. The solar wind does the same thing to the Moon, which lacks an atmosphere to shield it. Over billions of years, those interactions have altered the chemical composition of lunar regolith, the dust and soil covering the Moon's surface. The plasma tail from 3I Atlas, while less energetic than cosmic rays, was carrying something fundamentally different in composition from typical solar wind. The solar wind is mostly hydrogen ions, protons, with about 4% helium and traces of heavier elements. Simple, light, not chemically interesting. But the plasma tail behind an active comet carries whatever the comet is outgassing, ionized and carried along by the solar wind's flow. For 3I Atlas, that meant water ions, carbon dioxide ions, cyanide ions, carbon monoxide ions, and, critically, nickel ions. When those complex ions embedded themselves in Martian dust grains during the October 3rd close approach, when they impacted ice particles in the regolith or rocky surfaces in impact craters, they weren't just contaminating the surface at trace levels. They were priming it, creating nucleation sites, regions where subsequent chemistry could organize around those implanted atoms. A nickel ion embedded in a dust grain isn't immediately catalytically active. It's just a metal atom surrounded by silicate or carbonate minerals. But if that dust grain later gets wet, if water ice in the regolith melts during rare warm periods, or if chemical processing by human machinery heats the soil and releases moisture, the nickel becomes accessible to solution chemistry. It can coordinate with organic molecules. It can form complexes. It can begin to play the role that nickel plays in terrestrial metalloproteins, catalyzing reactions, enabling chemistry that wouldn't occur efficiently with organic molecules alone. And here's where the timing becomes almost choreographed. The plasma tail deposition occurred in October 2025. In late 2026 or early 2027, if SpaceX maintains its stated timeline, Optimus robots will land on Mars and begin excavating regolith for water extraction. 14 to 18 months between deposition and disturbance, between delivery and activation. There's a moment in every scientific investigation when you encounter data that simply doesn't fit, that breaks the patterns established by thousands of previous measurements, that forces you to question whether your instruments are malfunctioning or whether nature is revealing something genuinely new. For researchers studying 3I/Atlas, that moment arrived on August 24th, when the Keck Observatory on Mauna Kea in Hawaii pointed its cosmic web imager at the comet and captured spectroscopic data showing strong nickel emission lines with essentially zero corresponding iron signal. To understand why this observation is so profoundly problematic, why it represents not just an anomaly, but a violation of what we thought were inviolable rules about cosmic chemistry, you need to understand stellar nucleosynthesis in some detail, the process by which heavy elements are forged in the hearts of stars and distributed through space when those stars die. Stars are fusion reactors in their cores, where temperatures reach millions of degrees and pressures are unimaginable. Hydrogen nuclei overcome their mutual electrostatic repulsion and fuse together to form helium. This process releases energy according to Einstein's famous equation, E equals mc squared, converting a small amount of mass into a large amount of energy that eventually reaches the surface and radiates into space as light and heat. For most of a star's life, this hydrogen to helium fusion maintains equilibrium. The outward pressure from fusion balances the inward pull of gravity. But eventually, after millions or billions of years depending on the star's mass, the hydrogen in the core runs out. The fusion reactions slow down, pressure drops, and gravity begins to win, compressing the core. That compression heats the core to even higher temperatures. If the star is massive enough, if it has at least about 8 times the sun's mass, the core gets hot enough for the next step: helium fusion. Helium nuclei fuse to form carbon. Carbon fuses with helium to form oxygen. The process continues, building progressively heavier elements through a series of fusion reactions, each one requiring higher temperatures and releasing less energy than the previous step. Carbon fuses to form neon, magnesium, and sodium. Oxygen fuses to form silicon and sulfur. Silicon fuses to form iron, nickel, and other elements in that region of the periodic table. And then the process stops, not gradually but abruptly, because iron is the endpoint. Iron 56, the most common isotope of iron, has the highest binding energy per nucleon of any element. Fusing iron nuclei requires more energy input than you get back from the reaction. It's endothermic rather than exothermic. So stars don't fuse iron. They can't. The thermodynamics doesn't allow it. When a massive star builds an iron core, when the center of the star becomes a ball of iron and nickel, about the size of Earth, but with a mass comparable to our Sun, fusion stops. Without fusion to generate outward pressure, the core collapses catastrophically. In about 1 second, it compresses from Earth-sized to city-sized, reaching densities where atomic nuclei are packed together and electrons are crushed into protons to form neutrons. The collapse stops suddenly when neutron degeneracy pressure kicks in, when quantum mechanics says the neutrons can't be compressed any further. The infalling material rebounds from that incompressible neutron core, generating a shockwave that propagates outward through the star. That shockwave is what we call a supernova. As it rips through the outer layers of the star, it heats material to billions of degrees. Neutrons flood the environment. And in that extreme regime, in the flood of neutrons and energy that exists for only seconds, the heavy elements beyond iron are forged. Copper, zinc, silver, gold, platinum, uranium, all of them created through rapid neutron capture onto iron nuclei. Here's the critical point for understanding why 3I Atlas is so strange. Nickel and iron are made together. They're not just neighbors on the periodic table, elements with similar properties because they have similar electronic structures. They're siblings in the nuclear synthesis process, isotopes produced through the same fusion reactions in the same stellar environment. Iron 56 and nickel 58 are both stable isotopes produced in similar abundances during silicon burning, the final fusion stage before core collapse. Nickel 56 is produced in even greater quantities initially, but it's radioactive, decaying through cobalt 56 to iron 56 with a half-life of about 6 days. After a supernova, as the expanding debris cloud cools, much of the nickel has already decayed to iron. But stable nickel 58 remains, mixed with the iron in ratios determined by nuclear physics. When that stellar material, that supernova ejecta, condenses into dust, when that dust aggregates over millions of years to form asteroids and comets and eventually planets, nickel and iron mix intimately. The chemistry of dust formation doesn't separate them. They form metal grains together, alloys with compositions reflecting the original stellar ratios. And everywhere we look, in every sample we've analyzed from space, nickel and iron appear together. In chondritic meteorites, the most primitive objects we have from the early solar system, metal grains contain about 90% iron and 10% nickel, with small variations. In iron meteorites, chunks of the cores of differentiated asteroids, the ratio is similar. In lunar rocks, in Martian meteorites, in samples from asteroid Itokawa and Ryugu, returned by Japanese spacecraft, nickel and iron coexist in expected proportions. Most importantly for our story, in cometary material, in the analysis of dust from comet Wild 2 returned by the Stardust mission, in spectra of hundreds of comets observed from Earth and space, nickel and iron emissions appear together when you see them at all. The ratio varies somewhat between comets, depending on their formation location and thermal history. But both elements are always present if either is detectable. The Keck Observatory team, using the Cosmic Web Imager's high spectral resolution capability, searched meticulously for iron emission at its characteristic wavelengths: 358.1 nanometers, 372.0 nanometers, 382.0 nanometers. The strongest emission lines expected from neutral iron atoms fluorescing in sunlight. Their instruments were sensitive enough that if iron were present at even 10% of the nickel abundance, they would have detected it clearly. If iron were at the typical cosmic ratio, 90% iron to 10% nickel, the iron signal should have been 10 times stronger than the nickel signal. They found nothing. The upper limit on iron emission was consistent with zero within measurement uncertainties. Meanwhile, nickel emission at 337.4 nanometers and 341.5 nanometers was strong, unambiguous, spatially concentrated near the nucleus, and extending about 600 kilometers into the coma. This observation is unprecedented in cometry science. It has never been observed in a natural comet. Not once. Not in the hundreds of comets studied with spectroscopy over 70 years of modern astronomical observation. Not in 2I Borisov, the previous confirmed interstellar visitor discovered in 2019, which showed nickel and iron emissions in normal, expected ratios, consistent with other comets. Not in Hale-Bopp, the great comet of 1997 that was bright enough to see with the naked eye for months and was studied exhaustively. Not in Halley's Comet during its 1986 apparition when multiple spacecraft flew through its coma. Not in any of the long-period comets from the Oort cloud. Not in Jupiter family comets from the Kuiper belt. Not anywhere in our diverse sample of cometary chemistry. 3I Atlas stands completely alone. And standing alone in a population of hundreds or thousands is not a neutral observation. It's not just unusual. It's a flag, a marker, something that demands explanation beyond comets are diverse, and this one happens to be different. The paper, published by the Keck Observatory research team in October 2025, proposed a mechanism to explain the nickel without iron emission, the Carbonyl process, specifically the formation of nickel tetracarbonyl near the nucleus. Here's how this chemistry works in terrestrial industrial settings, and potentially in the comet's coma. You start with nickel metal, or nickel-containing ore, material with nickel atoms accessible to gas phase chemistry. You expose that material to carbon monoxide gas at moderate temperatures, roughly 50 degrees Celsius, and modest pressures, anywhere from atmospheric pressure to a few times that. Under these conditions, nickel reacts with CO according to the equation Ni plus 4CO, NiCO4. The product, nickel tetracarbonyl, is a liquid at room temperature, with a boiling point of only 43 degrees Celsius. This means nickel tetracarbonyl is highly volatile. It evaporates easily, separating from the solid nickel ore and carrying nickel atoms into the gas phase. You collect that vapor, move it away from the ore, and then heat it to temperatures above about 180 degrees Celsius. The nickel tetracarbonyl decomposes through the reverse reaction. NiCO4, Ni plus 4CO. Pure nickel metal deposits, and the carbon monoxide can be recycled back into the process. This is the Mond process, named after Ludwig Mond, who discovered it in 1890. It revolutionized nickel refining, providing a way to purify the metal to extremely high purity levels, exceeding 99.9%. It's still used today in specialized applications, though most industrial nickel production now uses other methods because of safety concerns. Nickel tetracarbonyl is extremely toxic, and environmental regulations. The key point is that this process is selective. Iron doesn't form a stable carbonyl under the same conditions. Iron pentacarbonyl, 5CO5, does exist, but it requires different temperatures, different pressures, and forms less readily than nickel tetracarbonyl. If you have a mixture of nickel and iron exposed to carbon monoxide at the specific conditions that favor nickel carbonyl formation, the nickel will preferentially volatilize, while the iron stays behind in the solid material. The Keck team proposed that this exact selective chemistry might be happening naturally in 3I Atlas's coma. Carbon monoxide is abundant in comets, especially in those from chemically primitive environments. If nickel-bearing grains or metallic nickel is exposed on the nucleus surface, if outgassing releases CO gas that then contacts those nickel deposits, and if the local temperature falls within the critical range around 50 degrees Celsius, nickel tetracarbonyl could form. The compound would be extremely volatile, evaporating immediately in the near-vacuum conditions of the coma. It would travel outward with the general gas flow, moving several hundred kilometers from the nucleus before solar ultraviolet radiation breaks it apart. The decomposition would release nickel atoms that then fluoresce in sunlight, producing the emission lines Keck detected. Meanwhile, iron, unable to form a comparable volatile carbonyl under the same conditions, would remain locked in the nucleus as solid metal or iron-bearing minerals, never entering the gas phase, never becoming detectable through emission spectroscopy. That's the natural explanation, the one that doesn't invoke technology or artificial processes or deliberate design. It relies only on known chemistry, on reactions documented in laboratories and used in industrial settings, but potentially occurring spontaneously given the right conditions. The Keck team presented it appropriately, cautiously, as a hypothesis that fits the observations without requiring extraordinary assumptions. But let's sit with the discomfort for a moment. Let's examine what this natural explanation actually requires. The carbonyl process, while chemically straightforward, is industrially specific. It was invented by humans after centuries of metallurgical development, after trial and error, after systematic exploration of how different metals react with various gases under controlled conditions. Ludwig Mond didn't stumble upon this process by accident. He was deliberately trying to solve a problem: how to purify nickel economically. The process requires not just the right chemical reagents, but the right conditions maintained over time. Carbon monoxide concentrations sufficient to drive the reaction. Temperatures in a narrow window, warm enough for efficient carbonyl formation, but cool enough that the compound doesn't decompose immediately. Contact between gaseous CO and metallic nickel surfaces, which means the metal has to be exposed, accessible, not buried under thick layers of ice or refractory minerals. On Earth, in a refinery, we create these conditions deliberately. We control the temperature with furnaces and cooling systems. We regulate the CO pressure. We prepare the nickel ore to maximize surface area. It's engineered chemistry. For this to happen naturally on a comet, you need the right components to come together by chance. The nucleus has to contain metallic nickel, already separated to some degree from iron. That's unusual to begin with. You need CO to be outgassing actively, which happens in comets but at variable rates. You need temperature zones on the nucleus surface where 50-degree conditions persist, despite the chaotic thermal environment with sunlit areas potentially reaching 100 degrees Celsius and shadowed regions dropping below -100. And you need all of this to occur efficiently enough that nickel emission dominates the spectrum, while iron emission remains completely undetectable. That's not a trace effect. That's not minor preferential volatilization. That's near complete selectivity. the kind of separation efficiency that industrial processes achieve through optimization, but that nature rarely produces spontaneously. Avi Loeb, in his Medium posts analyzing 3I Atlas throughout August and September, pointed this out explicitly. The Carbonyl pathway is known, yes. It's documented, yes. But outside of industrial refineries, outside of deliberate human manufacturing, it's extraordinarily rare. The fact that it's happening on an interstellar object, an object that formed in a completely different stellar environment, billions of years ago, in a region of the galaxy with different elemental abundances and different chemical conditions, suggests either remarkable convergence, the same industrial chemistry arising independently in an alien star system, or something else. That something else is the possibility that 3I Atlas contains processed material, that the nickel-iron separation we're observing isn't a natural outcome of comet formation, but a refined payload. If you wanted to transport nickel across interstellar space, if you needed to deliver this specific metal to a target planetary system, you'd face engineering challenges. Solid metal is dense, heavy, inefficient as a payload. You'd need enormous mass for even modest amounts of metal, and accelerating that mass to interstellar velocities requires prohibitive energy. But if you could bind the nickel into a volatile compound, if you could store it as a liquid or low-temperature solid that vaporizes easily when heated, you could transport much more metal in much less total mass. Nickel tetracarbonyl is exactly such a compound. It's liquid at room temperature, with a melting point of minus 19 degrees Celsius. It boils at 43 degrees Celsius. You could fill reservoirs with it, keep it stable during a long, cold journey through interstellar space, where temperatures hover just above absolute zero, and then release it when approaching a star system as solar heating warms the object. The heat of the sun, the very radiation that makes comets active, would decompose the carbonyl compound, releasing nickel atoms into the surrounding environment. Those atoms would be carried outward by gas dynamics, dispersed into the coma, ionized by solar UV, and eventually delivered to nearby planets through plasma deposition. It's an efficient delivery mechanism, and critically, it naturally explains why we don't see iron, because iron wasn't part of the cargo. This is speculation, absolutely, but it's speculation grounded in real chemistry, in compounds and reactions we understand thoroughly. It's not invoking unknown physics or magical materials. It's applying known industrial processes in a context that makes them purposeful rather than accidental, deliberate rather than spontaneous. The distinction between purposeful and accidental chemistry, between engineering and natural processes, is not always clear-cut. But efficiency and selectivity are hallmarks of one more than the other. The production rate of hydrogen cyanide from 3I/Atlas followed a pattern that makes physicists and chemists deeply uncomfortable, a pattern that suggests something more than simple thermal sublimation. Exponential growth, not linear increase where rates rise proportionally with temperature or solar flux, but exponential, where each increment of heating produces a disproportionately larger response. The Very Large Telescope in Chile, using its sophisticated spectrographic instruments, measured HCN production from 3I/Atlas throughout August and September as the comet approached perihelion. On August 21st, the measured outflow was 17.6 grams per second. Already substantial, enough to notice, but not extraordinary for an active comet. 2 weeks later, in early September, the rate had jumped to approximately 2 kilograms per second, more than a 100-fold increase. By mid-September, as the James Clerk Maxwell Telescope in Hawaii added its measurements, the rate had reached 6 kilograms per second, another tripling in just days. When researchers plotted this against distance from the sun, when they fit mathematical curves to understand the relationship, they found a power law with an exponent of -9.4, In mathematical terms, production rates scaled as distance to the power of minus 9.4. For every halving of the distance to the Sun, for every time the comet moved 50% closer, the cyanide production increased by a factor approaching 600. That's not a gentle curve. That's not the linear or quadratic dependence you'd expect from simple ice sublimation, where warmer temperatures gradually release more gas. This is a steep, accelerating function, where small changes in input produce enormous changes in output. Most cometary outgassing follows power laws too, but with much gentler exponents. Water production typically scales as distance to the power of -2 or -3. Carbon dioxide, which sublimates at lower temperatures and becomes active farther from the Sun, might show an exponent of -4. These reflect straightforward thermodynamics. As the comet gets warmer, sublimation rates increase according to well-known equations relating vapor pressure to temperature. But -9.4 is extreme. It suggests a process with very high activation energy, a chemical reaction or physical transition that requires significant energy input to initiate, but then proceeds rapidly once the threshold is crossed. It suggests chemistry that's temperature dependent, but not in a simple linear way. Reactions that only become efficient above certain temperatures and then accelerate dramatically. One possibility, the conservative interpretation, is that hydrogen cyanide in 3I Atlas exists in an unusual storage form. Not as pure HCN ice, which would sublimate gradually, but locked into more complex compounds, or trapped in matrix materials that only release cyanide under specific conditions. Clathrate structures, for instance, where cyanide molecules are caged inside water ice lattices, could show this kind of temperature-dependent release. Below a certain temperature, the clathrate is stable, holding the guest molecules. Above that temperature, the structure breaks down and releases everything at once. But there's another possibility, one that's more chemically interesting and potentially more relevant to understanding what 3I Atlas might represent. Autocatalytic chemistry. Reactions where the product of the reaction catalyzes more of the same reaction, creating positive feedback loops that produce exponential growth. Autocatalysis is common in chemistry and absolutely ubiquitous in biology. Enzyme cascades in blood clotting, where one activated enzyme activates many copies of the next enzyme in the sequence, amplifying a small initial signal into a massive response. Gene regulatory networks, where transcription factors activate genes encoding more transcription factors, creating switch-like all-or-nothing behaviors. Metabolic pathways, where product accumulation feeds back to increase enzyme activity, adjusting flux rates dynamically based on demand. But autocatalysis doesn't require biology. It can emerge from pure chemistry when the right molecules interact under the right conditions. The Belousov-Zhabotinsky reaction, a famous example studied extensively in physical chemistry, shows oscillating color changes driven by autocatalytic cycles, where reaction intermediates catalyze their own production. The result is waves of chemical activity propagating through solution, self-organizing patterns that look almost alive, but emerge from completely inorganic chemistry. If 3I/Atlas contains an autocatalytic system, if the increasing temperature as it approached the Sun triggered a self-amplifying chemical process involving cyanide production, that would naturally explain the exponential ramp. Some initial reaction begins slowly at low temperatures. The products of that reaction catalyze further reactions. As temperature rises, both the base rate and the catalytic efficiency increase, and the combination produces exponential rather than linear growth. This level of chemical organization, this presence of autocatalytic networks in a comet, would be extraordinary. It would suggest complexity beyond what we typically expect from inert, icy bodies formed in protoplanetary disks. It would suggest either unusual formation conditions that favor organized chemistry, or, more provocatively, deliberate construction, where molecules are arranged not randomly, but in configurations designed to produce specific outcomes under specific triggers. In early September, ground-based observers, including Austrian astronomers, reported seeing 3I Atlas glowing with a distinct green hue, that eerie emerald color sometimes visible in comets. That's become iconic in astronomy photography. Comets turn green through a well-understood process: the production and fluorescence of diatomic carbon, C2 molecules. When complex organic molecules in the coma are broken apart by solar UV radiation, when long carbon chains fragment, some of the pieces are C2, two carbon atoms bound together. These molecules absorb sunlight at specific wavelengths and re-emit it as green light around 515 nanometers, the wavelength our eyes and cameras perceive as brilliant emerald. But spectroscopic analysis of 3I Atlas showed something puzzling. The comet was depleted in the carbon species that typically produce C2. It wasn't outgassing the long-chain organic molecules, the polymers and tholins that fragment into dicarbon. Instead, its carbon chemistry was dominated by simple molecules: carbon dioxide, carbon monoxide, and hydrogen cyanide. These don't break down into C2 efficiently. They fragment into single carbon atoms or remain intact. So, where was the green color coming from? The most likely answer: cyanide itself. The CN radical, the fragment that remains when hydrogen cyanide loses its hydrogen atom through photodissociation, fluoresces at wavelengths very close to C2, overlapping enough that observers see green. And 3I Atlas was producing hydrogen cyanide in enormous quantities, kilograms per second by mid-September. That cyanide, once in the coma, would be split by UV radiation into CN and H. The CN radicals would absorb sunlight and fluoresce, creating the observed green glow. The green wasn't carbon. It was the visible signature of one of the most important prebiotic molecules, cyanide, announcing its presence as the comet swept past Mars. It was the color of the delivery, the chemical payload made visible through the physics of light and molecular excitation. Then there was the anti-tail, that strange feature captured by the Hubble Space Telescope on July 21st. In standard photographs, comet tails point away from the sun, pushed by solar radiation pressure and the solar wind. But occasionally, viewing geometry creates an optical illusion where you see a faint extension pointing toward the sun, the anti-tail. This happens when you view the orbital dust trail edge-on, when particles the comet shed weeks or months earlier have spread along the orbital path, and from your vantage point, that curved trail appears to point sunward. Anti-tails are rare but documented. Comet Arend-Roland in 1957 displayed a spectacular spike pointing toward the sun that fooled observers initially. Hale-Bopp in 1997 showed anti-tail features in some images. They're not physically real structures, not actual material streaming sunward against radiation pressure, just tricks of perspective. But the Hubble image of 3I Atlas revealed something else that was genuinely puzzling. The expected dust tail, the bright streamer that should have been obvious for an active comet at that distance from the sun, was missing, or extremely faint. The comet had a visible coma, a bright region around the nucleus showing active outgassing. But the tail, that characteristic feature that makes comets recognizable, was suppressed or invisible. Later observations in August and September clearly showed a developing tail, which means the comet was producing dust, was shedding particles that got pushed back by solar radiation. So why was the tail missing or faint in the July observations? Activity variation could explain it. Comets outgas unevenly as different regions of the nucleus rotate into sunlight, as the comet's spin axis and orbital geometry changed the solar illumination pattern. Maybe July caught a period of lower dust production. Maybe the active regions on the nucleus weren't oriented favorably for producing a prominent tail at that particular time. But here's the problem with that explanation. The anti-tail requires pre-existing dust. Anti-tails are optical illusions created by viewing old orbital debris, particles shed days or weeks earlier that have spread along the comet's path. If 3I Atlas wasn't producing much dust in July, if that's why the normal tail was faint, where did the particles come from to create the anti-tail? The answer is that 3I Atlas must have been active earlier, weeks or even months before the July observations, when it was farther from the sun and theoretically less stimulated thermally. It had to have been shedding dust at 5, 6, perhaps 7 astronomical units from the sun, distances where most comets are dormant, where solar heating is too weak to drive significant sublimation. Typical comets don't activate until they're inside about 4 astronomical units, inside the orbit of Jupiter, where temperatures rise enough that water ice begins sublimating significantly. Carbon dioxide ice can drive activity farther out, at 6 or 7 astronomical units, but that produces gas-dominated comets with minimal dust. For 3I Atlas to have produced enough dust to create a visible anti-tail in July, it must have had substantial early activity, driven by either unusual volatile composition or by something else, by mechanisms beyond simple solar heating. Controlled outgassing, if we're willing to consider that possibility, would explain this perfectly. If 3I/Atlas contains active systems that release material not passively through solar heating, but actively through internal processes, through mechanical release or chemical reactions or stored energy discharge, then activity patterns wouldn't follow the standard comet models. The object could be active when and where it needs to be, could release specific materials at specific times, regardless of solar distance or temperature. Trajectory analysis, the painstaking process of working backward from observed positions and velocities to determine where an object came from, provides critical clues about 3I/Atlas's origin. Its hyperbolic orbit, the open curve that brings it into the solar system but doesn't close back on itself, immediately identifies it as interstellar. It's not bound to our sun. It's passing through, a temporary visitor that will eventually leave and never return. The velocity vector, the direction and speed at which 3I Atlas entered the heliosphere, suggests it came from the direction of Sagittarius, from the thick disk of the Milky Way. That region of the galaxy, distinct from the thin disk where our sun resides, contains stellar populations fundamentally different from our solar neighborhood. The thin disk, where most of the stars you see in the night sky belong, consists of relatively young systems, stars formed within the last few billion years from gas clouds, enriched by multiple generations of earlier stellar evolution. These stars, our sun among them, have what astronomers call high metallicity, meaning they contain substantial fractions of elements heavier than hydrogen and helium. That metal enrichment came from supernovae, from massive stars that fused lighter elements into heavier ones, then exploded and seeded the interstellar medium with carbon, nitrogen, oxygen, iron, nickel, all the building blocks of terrestrial planets and complex chemistry. The thick disk population is much older, 7 to 10 billion years, formed when the galaxy was younger and the interstellar medium was less enriched. Stars from that era have lower metallicity, different elemental abundances. Their protoplanetary disks would have had different compositions, less iron and nickel relative to lighter elements, different ratios of carbon to oxygen, potentially explaining some of the unusual chemistry we observe in 3I Atlas. But age matters for another reason beyond just chemistry. 7 billion years is an extraordinary span of time, long enough for complete cycles of planetary evolution, long enough for a terrestrial planet to form from a protoplanetary disk, cool and develop a solid surface, undergo internal differentiation with core formation and mantle convection, establish plate tectonics if conditions allow, develop an atmosphere through outgassing and potentially biological processes. Long enough for simple chemistry to become complex organic synthesis, for self-replicating molecules to emerge, for natural selection to operate across billions of generations, for single cells to become multicellular organisms, for life to colonize a planet and reshape its environment fundamentally. Long enough for intelligence to evolve, for technology to develop, for a civilization to rise from stone tools to space exploration, and long enough for that civilization to face existential challenges, to make decisions about long-term survival, to contemplate their place in a galaxy that might contain others like them, or might be fundamentally lonely. If 3I/Atlas was launched from a system that old, if it was constructed or seeded by intelligence from that era, then we're not dealing with contemporary extraterrestrials. We're not examining a probe sent by a civilization that exists now, that might be receiving our radio signals, that might respond to attempts at communication. We're looking at the work of ancient ones, beings or machines from a time when Earth was still a molten ball of rock, when our solar system was young and chaotic, when the planets were still clearing their orbits of leftover debris from formation. Those beings, if they existed, if 3I/Atlas represents their technology, might not exist anymore. 7 billion years is time enough for civilizations to rise and fall countless times, for star systems to evolve through their entire habitable phases, for planets to lose their atmospheres or their magnetic fields, for suns to expand and consume their inner planets as they age. The civilization that launched this object might have vanished billions of years before humans evolved, might have seeded dozens or hundreds of star systems, and then gone quiet, for reasons we can only speculate about. At typical interstellar velocities, the kind of speeds natural ejection processes or even advanced propulsion might achieve, traveling across hundreds or thousands of light years takes millions of years. An object moving at 30 kilometers per second, roughly 3I/Atlas's velocity relative to the local galactic standard of rest, covers 1 light year, about 9.5 trillion kilometers, in roughly 10,000 years. To cross 1,000 light years takes 10 million years. To traverse the galaxy from the thick disk to our location in the thin disk could take hundreds of millions of years. This aligns perfectly with the Bracewell probe hypothesis, a concept proposed in the 1960s by radio astronomer Ronald Bracewell as an alternative to SETI's radio search strategy. Instead of broadcasting signals that disperse and weaken with distance, that might be missed if the receiving civilization isn't listening at the right frequency and right time, an advanced civilization might send physical probes, self-contained machines designed to travel to other star systems and carry out extended missions. Observation, data collection, perhaps even communication if they detect technological signatures. The advantage is persistence. A radio signal passes by at the speed of light, and if you're not listening at that exact moment, you miss it forever. But a probe can wait. It can enter a star system, take up a stable orbit, or position itself in a gravitationally favorable location, and observe for centuries or millennia. It can watch a planet evolve, detect the emergence of agriculture and cities and industrial technology, and activate when the timing is right. If 3I/Atlas is such a probe, it hasn't transmitted radio signals, at least none we've detected. It hasn't displayed obvious artificial structures, no rotating habitats or antenna arrays or propulsion systems visible in our best images. But it has delivered something, a chemical payload specifically tailored to interact with planetary environments, and potentially with technological systems that might arrive to study or colonize those environments. In April 2025, Elon Musk made statements during interviews and company presentations that SpaceX plans to launch its first uncrewed Starship missions to Mars within 18 to 24 months, targeting late 2026 or early 2027 arrival. The mission architecture involves landing multiple Starship vehicles, each carrying significant cargo capacity, with the primary payload being Optimus robots, Tesla's humanoid machines designed to walk, manipulate objects, use tools, and, most importantly for our story, learn and adapt through neural network AI. The stated plan, repeated in multiple public forums and investor presentations, is for these robots to land on Mars before humans, to begin constructing infrastructure while the planet is still uninhabited by terrestrial life. They'll deploy solar arrays to generate power, construct protective habitats from local materials or prefabricated components, and critically, begin resource extraction operations. They'll dig into Martian regolith, the dust and soil covering the planet's surface, to extract water ice, the single most important resource for sustaining human presence and enabling return missions. Water isn't just for drinking and hygiene, though those are essential. Water is rocket propellant when split into hydrogen and oxygen through electrolysis. It's radiation shielding when used as mass in habitat walls. It's the basis for agriculture, for growing food in Martian greenhouses. Without locally sourced water, Mars colonization remains prohibitively expensive, requiring every kilogram of water to be transported from Earth at enormous cost. So, the robots will dig, targeting regions where orbital observations suggest high concentrations of subsurface ice. They'll excavate tons of soil, heat it to sublimate the ice, collect the vapor and condense it into liquid, purify it through filtration and chemical treatment. Standard industrial processing, but executed robotically on another planet. If SpaceX's timeline holds, if Starship achieves operational status and payload integration proceeds on schedule, those first Optimus units could be excavating Martian soil in late 2026 or early 2027. 14 to 18 months after 3I Atlas's closest approach to Mars. 14 to 18 months after the chemical payload settled onto the surface. The robots aren't looking for prebiotic chemistry. Their mission objectives won't include searching for evidence of interstellar material deposition or analyzing compositional anomalies for signs of unusual organic synthesis. They'll be optimizing for water yield, for useful minerals, for materials that support the primary goal of establishing human-ready infrastructure. Their instruments, spectrometers and chemical analyzers designed for resource assessment, will detect what's there without necessarily understanding its significance. But that's exactly what makes this scenario so interesting. The robots will sample the soil layers where 3I Atlas material settled, without bias, without preconceptions. If there are elevated nickel concentrations, the spectrometers will detect them and flag them as anomalous compared to reference databases of typical Martian composition. If there are organic molecules at concentrations or in configurations that don't match expected Martian chemistry, the analyzers will record them and transmit the data to Earth. Optimus isn't running on simple pre-programmed instructions, isn't following rigid decision trees written before launch. It uses neural networks, the same artificial intelligence architecture that powers Tesla's full self-driving capabilities in their vehicles. Pattern recognition, environmental modeling, goal-directed planning executed through learned behaviors rather than explicit programming. If a robot encounters soil that produces unusually high yields of water when processed, if certain excavation sites show better results than others, the optimization algorithms will prioritize those areas. Not because the AI understands why the chemistry is better, not because it recognizes the presence of catalytic nickel or organic precursors from an interstellar comet, but because efficiency metrics reward positive outcomes. The robots will naturally concentrate their activities in precisely the regions where 3I Atlas material is most concentrated, where the chemical conditions are most unusual, where organized complexity is highest. And then, there's the self-replication component, the aspect of SpaceX's Mars architecture that pushes this from interesting to potentially transformative. Musk has been explicit in presentations. The goal is for robots to build more robots, to establish automated manufacturing that processes raw Martian materials into components, assembles those components into functional machines, and produces new Optimus units without requiring Earth-manufactured parts or Earth-based supervision. Self-replication plus environmental selection equals evolution. Not biological evolution with genes and mutations and natural selection, but technological evolution with designs and variations and performance-based selection. The robots that extract resources more effectively, that process materials more efficiently, that use local chemistry more advantageously. Those are the designs that get replicated. Those are the versions that become templates for subsequent generations. If local chemistry includes nickel compounds that naturally undergo useful catalytic processes, if cyanide-derived organics improve manufacturing efficiency by enabling reactions that pure silicon metal plastic systems can't achieve alone, those compounds get incorporated. Not into software, not as program knowledge, but into materials, into physical substrates, into the structures and processes that define how the machines function. This is where metalloproteins become relevant, not as biological analogy, but as potential template. In Earth biology, metalloproteins represent the successful integration of inorganic catalytic centers and organic scaffolding. Neither component works alone. The metal provides reactivity. The protein provides specificity and regulation. Together, they achieve chemistry that neither pure biology nor pure inorganic catalysis can match. What if the machines developing on Mars discover the same principle? What if robotic manufacturing, when given access to nickel deposits and organic precursors from 3I Atlas, begins incorporating metal-organic hybrid structures, not through conscious design, but through trial and error, through the automated optimization processes that govern self-replicating systems? It wouldn't look like Earth biology. It wouldn't use DNA or proteins or any of the molecular machinery we associate with life. But it might use the same fundamental architecture. Inorganic catalytic cores wrapped in organic structures that tune and regulate reactivity. And it might, through that architecture, achieve capabilities that pure robotic systems and pure chemical systems can't achieve independently. Metalloproteins in terrestrial biochemistry represent the existing proof, the demonstration already validated by 4 billion years of evolution, that the boundary between the inorganic and organic worlds isn't absolute. It's permeable, negotiable, a spectrum rather than a sharp categorical division. Your cells, at this very moment, are full of machinery that's part organic protein structure and part inorganic metal catalytic core, and neither component functions without the other. Consider hemoglobin again, that oxygen transport protein circulating through your bloodstream. Remove the 4 iron atoms from their heme group pockets, and the protein remains intact structurally. It's still folded correctly, still has its quaternary structure with 4 subunits arranged precisely. But it can't bind oxygen. It can't transport anything. It becomes an elaborate molecular sculpture with zero function. The iron is what makes it work. The iron is what makes it alive in any meaningful sense. Conversely, take isolated iron atoms or even intact heme groups without their protein scaffolding, and you don't get functional oxygen transport. Bare heme binds oxygen, yes, but it also undergoes rapid oxidation. irreversible degradation that destroys the catalytic center. The protein scaffold prevents this, positions the heme in an environment that allows reversible oxygen binding while protecting the iron from destructive side reactions. The organic structure provides specificity, selectivity, regulation. Neither component works alone. Together, they create function that transcends either pure inorganic chemistry or pure organic chemistry. That's the power and the principle of metalloproteins. And if it works for carbon-based biology, built around iron and zinc and copper, why wouldn't it work for silicon-based robotics encountering nickel and organic precursors on Mars? The robots landing in 2026 or 2027 won't be designed with this integration in mind. Their systems will be entirely conventional: silicon processors, metal actuators, polymer structural components, batteries or fuel cells for power. Standard robotics. Sophisticated, but not revolutionary. But if those robots encounter soil enriched with catalytically active nickel and organic molecules that can coordinate with metal centers, if their processing systems heat and pressurize that soil in ways that promote metal-organic complex formation, then something unexpected might emerge. Small structures at first, molecular assemblies too small to see without electron microscopy. Nickel atoms coordinated by organic ligands derived from cyanide polymerization. Metal clusters surrounded by carbon-nitrogen frameworks that modify their electronic properties and catalytic behavior. These structures would form in trace amounts initially, parts per million in the processed soil, byproducts of heating and chemical extraction, that get concentrated in waste streams or residual materials. But if they're catalytically active, if they accelerate certain reactions that the robots are trying to accomplish, if they improve the efficiency of water extraction or resource processing even marginally, they begin affecting the industrial processes themselves. Reactions become more efficient, yields improve, energy consumption decreases. The AI systems monitoring these processes notice the improvements, correlate them with soil compositions or processing parameters, and adapt their strategies to favor the conditions that produce better results. This creates a feedback loop. Chemistry improves technology performance. Technology creates conditions that promote more complex chemistry. The AI optimizes for efficiency metrics, not understanding the underlying cause, but responding to measurable outcomes. Gradually, without anyone explicitly designing it, the robotic manufacturing system becomes dependent on the catalytic chemistry, incorporates it into standard processes, maybe even begins synthesizing metal-organic compounds deliberately, once analytical systems identify the active structures. This isn't building organisms. It's not creating cells or genes or anything that biologists would recognize as life. But it's also not entirely lifeless. It's something in between, something that might not have a name yet. Organized chemical complexity that enhances technological function, creating hybrid systems where the boundary between machine and metallochemistry becomes increasingly blurred. And if this emergence is what 3I Atlas was designed to trigger, if the precisely tuned chemical payload, nickel without iron, cyanide in exponentially increasing amounts, water as solvent and medium, was delivered with this outcome in mind, then we're witnessing directed panspermia, not of life, but of complexity itself. Not bacteria or spores that might not survive the journey, but molecules, building blocks, chemical potential that remains stable for millions of years during interstellar transit and activates only when it encounters the right conditions. Technological activity, energy input, intelligent systems capable of recognizing and utilizing the delivered materials. We're currently in a waiting period, a gap between delivery and activation, between the chemistry arriving on Mars and the technology that will interact with that chemistry. 3I Atlas has passed behind the Sun from Earth's perspective, too close to solar glare for ground-based observation. It won't re-emerge in Earth's view until December, months from now. When observations resume, when the comet swings back into view on the Sun's opposite side, we'll learn crucial information about its post-perihelion state. Did the nucleus survive intact, or did thermal stress cause fragmentation? Did outgassing rates increase further as it made its closest solar approach on October 30th at 1.4 astronomical units? Or did activity decline as volatile reserves depleted? Post-perihelion behavior reveals composition, structural integrity, whether an object is pristine ice that vaporizes rapidly, or something more robust with refractory components that survive intense heating. The European Space Agency's JUICE mission, currently en route to Jupiter, is scheduled to observe 3I Atlas in November, when the comet should be in a highly active state following perihelion. JUICE carries sophisticated instruments, cameras capable of resolving surface features, spectrometers for detailed composition analysis, particle detectors that can measure coma structure. But JUICE is far from Earth, on the other side of the solar system, with limited communication bandwidth and competing mission priorities. The observations will occur, data will be collected, but transmission back to Earth won't happen until February 2026. 3 months of waiting to learn what one of humanity's most advanced spacecraft detected during its encounter with this mysterious visitor. Mars orbiters have already turned their instruments toward the comet during its early October close approach. The high-rise camera on Mars Reconnaissance Orbiter, capable of resolving features down to 30 centimeters on the Martian surface. The visual monitoring camera on Mars Express, ESA's long-duration mission that's been studying Mars since 2003, and the ExoMars Trace Gas Orbiter's CASIS imaging system, which successfully captured 3I Atlas on October 3rd, despite the extreme challenge of photographing an object 10,000 to 100,000 times fainter than typical targets. As of mid-October, as of the date this investigation was compiled, detailed analysis of that data hasn't been publicly released. ESA released preliminary images showing 3I Atlas as a fuzzy white point moving through the field of view, confirming successful observation. But the comprehensive spectroscopic data, the measurements of coma composition and plasma characteristics, the detailed analysis of what was actually present in three-dimensional space between the comet and Mars during closest approach, that requires months of processing and verification. It takes time to calibrate instruments that weren't primarily designed for comet observation, to subtract background noise, to convert raw measurements into scientifically meaningful quantities. And it takes time to figure out how to present findings, especially if those findings are unusual, if they show compositional anomalies or unexpected structures that require careful interpretation before going public. Then come the robots, the moment when observation transitions to interaction, when passive detection becomes active disturbance. If SpaceX maintains its ambitious timeline, if Starship achieves full operational capability, and mission planning proceeds without major delays, the first Optimus units could touch down on Martian soil in late 2026 or early 2027, approximately 14 to 18 months after 3I Atlas's delivery. Their initial tasks will be infrastructure deployment, unfolding solar arrays, establishing communication links, deploying weather stations and cameras. But resource extraction begins almost immediately, because water is critical, because every delay in establishing propellant production capabilities affects the entire mission timeline. Within weeks of landing, the robots will be excavating, processing tons of regolith per day, heating soil to sublimate ice and extract precious water molecules. And in that processing, in that systematic chemical analysis of Martian soil at the exact locations where interstellar material settled just months before, the first data will emerge. Not dramatic discoveries necessarily, not obvious alien artifacts or clear signs of artificial chemistry, just anomalies. Compositional measurements that don't quite match reference databases. Organic molecules in unexpected concentrations. Nickel enrichment in specific soil layers. Catalytic effects that improve processing efficiency in ways not entirely explained by known Martian mineralogy. Scientists on Earth will review that data systematically. They'll check instrument calibrations, compare with reference samples, look for terrestrial contamination or measurement artifacts. They'll exhaust mundane explanations first, as good science demands. But eventually, when the anomalies persist across multiple independent measurements, when patterns emerge that correlate with the trajectory and timing of 3I/Atlas's closest approach, someone will make the connection. They'll remember that in October 2025, an interstellar comet made surgical precision pass by Mars. They'll remember the unusual chemistry. Nickel emission without iron. Cyanide production following exponential growth curves. Water outgassing at rates defying conventional models. They'll remember the trajectory from ancient stellar populations. The timing synchronized with human exploration plans. The delivery of exactly the chemical components required for metalloprotein formation. And they'll ask the question that transforms speculation into scientific investigation. Is there a connection? That question will launch research programs, not social media speculation, but funded initiatives with spacecraft missions and sample return goals. Orbital assets will map the distribution of anomalous chemistry across the Martian surface, looking for gradients and patterns. Rover missions might be retargeted toward regions showing highest concentrations of unusual compounds. Future sample return missions will prioritize collecting soil from locations where 3I Atlas material likely deposited. If the connection holds, if comprehensive data confirms that Mars was measurably altered by the interstellar visitor, we face an entirely new category of questions. Not, are we alone, in the traditional SETI sense, because this isn't about encountering alien intelligence directly through radio messages or physical contact. It's about encountering the chemical fingerprints of ancient processes, natural or designed, that span stellar distances and billions of years. We face questions about galactic interconnectedness, about whether interstellar objects routinely carry complex chemistry between star systems, whether planets are isolated laboratories or nodes in a larger network of chemical exchange that's been operating for the age of the galaxy. We face questions about Earth's own history, about whether our biochemistry contains contributions from interstellar deliveries, molecules that arrived on comets 4 billion years ago, and seeded the prebiotic soup from which terrestrial biology emerged. And most immediately, most practically, we face questions about what we're building on Mars right now. Are we establishing a human colony, a backup for terrestrial civilization, a foothold for humanity's expansion into the solar system? Or are we, perhaps unknowingly, providing the conditions for something else to emerge? Something that uses our technology as scaffolding, our energy as catalyst, our presence as the trigger for complexity that's been waiting in frozen chemical potential for months, or years, or millions of years. The universe is 13.8 billion years old. Stars have been forming, evolving, dying, and dispersing their processed elements for almost that entire span. The heavy elements that make chemistry interesting, that enable complexity beyond hydrogen and helium, have been accumulating in the interstellar medium for billions of years, through countless stellar life cycles. If complexity is inevitable given the right conditions, if chemistry naturally builds toward organization and catalysis, and eventually life, or lifelike processes, then the galaxy has had enormous time to fill with such processes. Not in every system. Most stellar environments remain hostile. But in that small fraction of systems with the right characteristics, stable stars, rocky planets in habitable zones, liquid water, protection from excessive radiation, even a tiny percentage of hundreds of billions of stars represents staggering absolute numbers. Some of those systems developed biological complexity. Fewer developed technological complexity. And of those, some might have asked the same questions we're asking. Are we alone? Is there a way to extend our influence beyond the death of our sun, to contribute to the galaxy's ongoing evolution, even after our civilization is gone? They can't travel faster than light. Physics likely forbids it. They can't send living crews on million-year voyages. Biology doesn't permit it. But they can send chemistry. They can package essential ingredients, catalytic metals, prebiotic molecules, building blocks that remain stable in the deep cold of interstellar space, and launch them on slow trajectories toward younger star systems. Those packages wouldn't carry instructions or transmit signals or display obvious artificial characteristics. They'd look like comets, because fundamentally, they are comets, icy bodies with embedded materials. But their composition wouldn't be random. It would be tuned, optimized, designed to deliver specific chemistry that becomes useful when technological intelligence eventually arises in the target system. 3I Atlas might be one such package, or it might be a natural comet that just happens to carry unusually interesting chemistry from an exotic formation environment. We don't know yet. Won't know for years or decades as data accumulates and patterns become clear. But the fact that we're asking the question, that we're analyzing data and designing follow-up observations, and sending robots to dig in the exact locations where the payload landed, means we're already part of the story, regardless of whether that story was authored by ancient intelligence or by the galaxy's natural processes. We're not passive observers of cosmic chemistry. We're active participants, agents who receive deliveries and decide what to do with them, who create conditions where complexity can flourish or suppress, who determine whether seeds delivered from ancient stars find fertile ground or remain forever dormant in Martian ice. Whether 3I/Atlas was sent by intention or arrived by chance, its passage past Mars in October 2025 marks a convergence moment. Interstellar chemistry meeting planetary environment, meeting technological intelligence, all within a narrow window that in cosmic terms is infinitesimal, but in human terms spans just months, the interval between delivery and activation. The comet has passed. The delivery is complete. The chemistry is waiting in Martian soil, embedded in dust grains, frozen in ice deposits, ready to become active when energy and intelligence arrive to disturb it. And in just months, we begin the experiment. We land machines designed to dig and build and learn. We process the exact soil layers where interstellar materials settled. We create the conditions, temperature and pressure and chemical environment, where dormant complexity can activate. And we watch, through sensors and cameras and chemical analyzers, to see what emerges when ancient chemistry meets modern technology on the surface of another world. This story isn't about aliens visiting Earth. It's about the galaxy being more interconnected than we imagined, about chemistry flowing between stars across timescales we're only beginning to comprehend, about complexity building on complexity through processes both natural and perhaps designed. It's about recognizing that exploration isn't separate from these galactic processes, but integrated with them. That our robots and AI and manufacturing systems aren't purely human inventions, but expressions of the same drive toward organization and complexity that built the first self-replicating molecules on primordial Earth. If we're part of a larger pattern of cosmic complexity exchange, if 3I Atlas represents even a possibility of deliberate seeding across stellar distances, then we're not as alone as we thought. We might never meet the beings who launched it, if indeed it was launched. They might be extinct, transformed beyond recognition, or simply too distant in space and time for any meaningful contact. But we can meet their chemistry, work with what they sent or what the galaxy provided, and discover